Hey, this is John with Two Moose Home Inspections. During this video, we'll be discussing deck construction and how decks are inspected. And actually, while I have you here, I'll just give you the TLDR right now. After performing thousands of inspections, we have never seen a deck without defects, not even in new construction decks. What does this mean for the homeowner? Meh, not much, but if you want to learn about all the incorrect ways that almost all decks are built, then boy, is this the video for you. This video will be broken down into the impossibility of inspecting for code compliance, what it means to inspect a deck for intended function instead of code compliance, a full breakdown of how we inspect decks, and some additional considerations that deck owners and builders might want to be aware of. With that out of the way, let's dive in. Compared to the complexities of inspecting a house with engineered structures, HVAC, electrical, plumbing, roofing, and countless combinations of fixtures and appliances made from an unknown number of manufacturers to be inspected, it would be fair to say that during a home inspection, decks are one of the least complex components to be inspected. And that would be true. But before we dive into the intricacies of inspecting a deck, now might be a good time to illustrate why home inspectors are not code inspectors and help people understand the limitations a home inspector might encounter while inspecting even the most basic components of a deck. In regards to a deck inspection, the two most common questions we get are, was the deck built with a permit, and does it meet code? Essentially, these are the same question, since a permit is issued by the local government to ensure that a deck's construction follows a code that was adopted by that local government at that time. Since you can't start building a deck without a foundation, let's start there and determine if the footings for this hypothetical deck built in Breckenridge, Colorado are code compliant. Step 1. Soils. Complete a geotechnical evaluation to determine soil characteristics using an approved agency using an approved method. Unfortunately, as a home inspector, I don't have the budget of $1,000 to $5,000 to hire that approved third party for every deck that we inspect, nor do I have the 2 weeks to 2 months to wait for the report findings, but not all hope is lost. I could use table 401.4.1 of the IRC to determine load-bearing values of foundation materials, but I guess I would first need to know how to adequately identify classes of materials. Well, we are in the high Rockies, so I'll just go with bedrock as our class of materials and ignore all the differences in soil behavior between the peaks and the valleys of our topography and, just move on to the next step. Step 2, footing size. Determine the snow load pound per square inch value of the foundation of the deck using the Colorado Design Snow Loads document prepared by the Structural Engineers Association of Colorado Snow Load Committee. Okay, easy, so just scroll down here, find Breckenridge, and then bam, 80 pounds per square inch. Easy peasy. Next, determine the tributary area for each footing independent of each other footing by first measuring halfway between the nearest support member in 2 directions to normalize the span for a rectangle, and then convert that measurement of feet and inches into decimal feet, and then multiply by the length and the width of the area supported by the footing to find the square foot tributary area, and then round that number down, and then do this for every single footing. Then, by using table R507.3.1 of the IRC, cross-reference the load-bearing value of soils found in table R401.4.1 with the snow loads found in the Colorado Design Snow Loads document, and wait a second, well, it doesn't appear that the 80 pounds per square foot is on this table. Okay, well, no bother. Let's just follow the trend and make the footing a few inches wider so we can move on to the next step. Step 3, footing depth. Ensure the footing is not less than 12 inches below the undisturbed ground surface. So should I disturb the ground surface and ensure the footing was deep enough by using my bare hands, maybe a shovel? Let's just move on. Ensure the footing is protected from frost using one or more of the following methods. Extending below the frost line specified in table R301.2. Okay, this chart was not helpful, but a footnote says that I can check figure R403.1 subsection 1. Well, okay, figure R403.1 subsection 1 doesn't take into account an 80 pounds per square inch load of snow, but R301.2 did state that additional criteria shall be established by the local jurisdiction, which in this case would be Breckenridge, so let's try that out. Okay, so I guess depending on what subdivision I'm in, the snow load is actually between 90 and 100 pounds per square foot, not 80 pounds per square foot. And the frost line can fluctuate between 40 inches and 40 plus inches, whatever plus means. So do I need to dig down 40 or more inches into the ground to ensure that each footing is the correct depth? Let's see what the other criteria is first. Erecting on solid rock. Well, that isn't much better, so it sounds like after all that time and effort of trying to verify if the footing was built to code, unless I'm willing to dig until I hit solid rock or until I reach a depth of 40 plus inches, I won't know if the deck meets code. Okay, but if the deck was built with a permit, then the local government would have inspected to ensure the footing was the correct depth before pouring concrete, so I can at least see if it was built with a permit. First of all, if there was a permit issued, are we sure that the code inspector reviewed the engineered drawings to then be able to accurately measure the depth and the width of every hole prior to the concrete being poured back in 1997? Let alone for an inspection that was performed yesterday, considering that as of today, there are over 1,000 issued permits and another 800 plus permits that have been applied for that are being managed by government staff of 4 people, of whom only 2 are inspectors. It feels like they might be a little overworked. Let's ignore the whole line of thought about the quality of the permit inspection, and instead, let's just say you want to know if the deck was built with a permit. Unfortunately, without an in-person records request at the Breckenridge Building Department, which could take days to process, the oldest searchable permit in the Breckenridge database is from 1994, and the next oldest is from 1997. So if the deck that we're inspecting was built before that time, then I guess we would be out of luck, and we may never know if a permit was issued, let alone completed for the deck's construction. As we already discussed, we don't know what kind of soil the deck was built on, and the snow load in our area is off the charts, which means we have limited guidance to size footings. And then there's no way to determine if any of the footing's depths are below frost line without undermining the structure. So as it turns out, there is no practical way to determine if the footings, which are the foundation of the entire deck, which are arguably the most important part of the deck, meet even one of the outline code requirements. But even if we could, what code compliance standards would we be inspecting for? Consider that the 3 model code groups, Building Officials Code Administrators, Uniform Building Code, and the Standard Building Code, were merged to form the International Code Council in 1994 and published their first International Building Code, which included the International Residential Code, in the year 2000, and that every 3 years the ICC updates the IRC, and that each local government can choose to adopt any revision of the ICC model code at any time, and each local government can modify or ignore any part of any revision of the ICC model code, meaning we have no way to determine if the deck was built following the rules that were adopted at the time of construction. But I can assure you, I have never seen a deck in all my years of inspecting that was able to meet every modern standard provided by the IRC, not even new construction. Inspecting a deck almost seems hopeless until we change our mindset from inspecting for code to inspecting for intended function. If a deck functions as intended, then it almost doesn't matter what code was adopted and enforced at the time of the deck's construction. As we learned when we discussed code, engineers are responsible for a significant number of calculations that influence subtle considerations and modifications to a deck's construction that are normally hidden from the naked eye, such as fastening patterns, bracing, wood species, hardware, and many other factors. A deck that may appear to follow all modern building standards may not have been built using an engineer's drawing, but instead, and unfortunately, only using the builder's experience. So how do we inspect a deck for intended function? Regardless of the budget, it's safe to say that the intention of every deck builder is to build a safe deck, both from a pride in one's work and also an insurance cost perspective. No one wants to be responsible for a deck collapse. For a deck to be safe, a deck must be able to support the weight of itself and occupants without the risk of structural failure. Therefore, the underlying function of any deck is to resist loading. So what is loading? When we look at a deck, one of the first things we look for is a continuous load path. What this means is a load or a force to be transferred from the point of application to the foundation using structural components. Some loads are static, such as the weight of the structure, and those are called dead loads. Other loads are dynamic, such as walking across the deck, which is called a live load. Live loads are forces that are applied to the structures on and off during the life of the deck. This might also include snow, wind, furniture, and occupants. These loads don't just create compressive forces pushing down into the foundation, but instead they can cause complex interactions between structural components when vertical and lateral loads are applied. As you walk across the deck, you laterally load the deck away from your direction of travel, and when you stop moving, you laterally load the deck in the direction you were coming from. As you walk across the deck, you also apply a vertical load down, which applies a vertical load up somewhere else on the deck, which is called uplift. Loading a deck through normal use results in complex interactions between materials and fasteners, which may someday result in the eventual failure of the structure. Ideally, the deck should be constructed to manage vertical and lateral loads by providing a continuous load path through the structural components for any force to travel. But sometimes we see something we like to call rancher's ingenuity, which is effectively a non-standard solution to a problem that is often solved by using items from, around the property that were not intended to be used in the way that they're currently being used. Rancher's ingenuity solutions are readily identifiable, but they aren't necessarily considered to be a defect that needs repair or replacement. Remember, we're not inspecting for code, we're inspecting for intended function. If the deck appears to be safe enough to walk on, then we'll walk on the deck while paying very close attention to the sensations of movement we feel under our feet as we walk, bounce, and shift our weight. We also use our hands to feel movement when we push and pull on guardrails and posts. If the deck doesn't move in the slightest, then we can say that the deck functions as intended, regardless of the lack of modern building standards. If the deck exhibits unwanted movement, then the deck does not function as intended, and the deficiencies we identify will be in the report to show the method of failure that the deck is experiencing. Confusingly, we might identify and report a greater number of deficiencies for a safe and functional old deck that needs 0 repairs when compared to an unsafe, non-functional deck that should be repaired immediately. This is why we rate deficiencies by severity, to help clarify when a deck is or is not functioning as intended. In that example, the safe old deck may have a handful of notes discussing the age of the deck and the outdated construction methods, whereas the unsafe new deck might only have 1 note stating that the deck sways side to side while walking on it, which is a significant defect that may result in a complete structural failure. Now let's learn about how we identify functional issues with decks. We have seen so many decks that we have a really good idea of what's normal for our area, and for the most part, we can tell very quickly what deficiency the deck might have. When we first look at a deck, we look at the condition of the deck in general. Then we take into consideration if the deck is a bare minimum build using common lumber sizes, or does the deck use custom large format lumber. The fit and finish, along with the details and embellishments, can tell us a lot about the deck and its construction, but all decks age over time and not all decks age well. So let's keep a few things in mind when we take a look at this deck. Do the footings look robust and do they align with the posts? Does the deck appear to be over-engineered with thick structural members and well-supported and properly spaced joists? Do things appear to be properly connected using quality hardware? Do the fasteners seem to be appropriate for the application? Are the components of the deck custom built, or is it built from a kit? Are there any signs of loose connections? Are there any signs of corrosion? Are there any signs of decay? Are there any splitting or damaged structural members? Does the deck appear to be neglected or well maintained? Let's take a look at some areas of interest. The ledger board is the primary connection between the deck and the house. Ledger attachments should be anchored to the home to resist vertical and lateral loads. The use of nails is no longer an approved fastening method, and there are a significant amount of engineering considerations that affect the type of fasteners, fastening patterns, and the size of the ledger board that we would never know unless we had an engineered drawing. So all we can do is walk on the deck, shift our weight up and down, side to side, and forward and back, while looking for signs of movement or separation. If nothing indicates vertical or lateral movement, then the ledger board is good enough, even if it was attached with antiquated nails. Lateral load connections reduce the likelihood that the deck would separate from the home, and modern standards may lead you to expect 4 or even more of these connections per deck. Same as before, we would love to see these installed with every deck, but if the deck feels good and looks good, then it's good. Joist to ledger connections should resist rotational forces created by lateral loads and separation caused by lateral and vertical loads. Separation failures from uplift forces created by live loads acting on a cantilever are often more common than those caused by wind in our area. Toe-nailing is no longer considered an acceptable method of attachment, but many decks that were built prior to today were constructed using toe-nailing. Again, if it feels and looks good enough, then it's super good enough. Post footings should be supported by and anchored to concrete footings. Direct burial, concrete slabs, and precast concrete piers are considered to be inadequate. Footing should be 14 inches round and below frost depth, which is 40 inches or more in our area. However, the depth of the footing is obstructed by the grade, and the anchor hardware and 1-inch standoffs of non-pressure treated wood are normally also obstructed from view. In addition to our standard loading and unloading of the deck to feel for vertical movement, lateral movement, deflection, and bounce, we also apply a force directly to the post horizontally to check for movement. If the posts don't show signs of wood decay and there aren't any signs of upheaval or settling while looking from one end of the deck to the other, and the footings feel rock solid, then they're probably on solid rock. The size of the post should be determined by cross-referencing the tributary area the post is supporting by the species of lumber, by the height of the post to determine if the post should be a 4x4 all the way up to an 8x8 inch post. Considering that our area's snow load is up to 100 pounds per square foot and the chart that a builder would reference only goes up to 70 pounds per square foot, it's safe to say that almost all decks have undersized posts. So if the post appears to be supporting the load without signs of failure such as bowing, then it's probably fine. Beam to post connections must be able to resist uplift, lateral displacement, and vertical loading. The ends of the beam must have at least 1.5 inches of bearing on wood or metal and at least 3 inches of bearing on concrete or masonry, and the width of the beam must be fully bearing on the post. This means the decks we see that were constructed at a time when the shear strength of a few through bolts was considered acceptable is no longer considered acceptable. Obviously, we'll note the deficiency in our report, but if the deck functions as intended, then it's functional. Remember, just because we list something as a deficiency doesn't mean you or anyone else needs to do anything about it. We're just letting you know. Additionally, not all approved methods of fastening are visible after construction is completed. Some beams are solid wood and may utilize hidden timber screws, and other beams are constructed using a multi-ply beam assembly that may or may not meet modern nailing standards. If the beam to post connection appears to be supporting the structure without signs of movement and also has a well-supported continuous load path, then the connection is probably fine. Knee brace connections may be required to resist lateral loads, but some post-based installations eliminate the need for knee bracing. However, depending on the height of the post, knee bracing still may be required. You can normally feel when a deck needs to have knee bracing installed because the deck sways as you shift your weight laterally side to side. Joist to beam end connections should have at least 1.5 inches of bearing on wood or an approved joist hanger. They should resist vertical load uplift resulting from the full live load acting on the cantilever portion of the deck, and joist beam connections should resist lateral loads to prevent rotation and displacement. Sometimes blocking is required to prevent rotation, but if the joists appear to be well supported without signs of loose fasteners, rotation, separation, or displacement, then they're functioning as intended, even if they're toe-nailed in place. Guard posts should be fastened to the deck framing using a method that will resist the forces that are expected to be exerted on the guard post. Often, guard posts will only be attached to the rim joist, which results in the eventual failure of the guard post and rim joist. Guard posts should also not be any further than 6 feet apart. Guardrail to guard post connections should be between 36 to 42 inches above the deck surface. The guardrail assembly should be able to resist 200 pounds of horizontal force in any direction. Guardrails are required for walking surfaces located more than 30 inches from a lower surface at any point within 36 inches of an edge. So here's a question. Is a 29-inch fall any less dangerous than a 31-inch fall? Some decks that should have a guardrail installed don't, because it would hinder the beautiful view. So should that be considered a defect? Would the new owner decide to ruin their view to protect themselves from a 31-inch fall? I don't know. What do you think? Should a guardrail be installed? We'll still call it out as a deficiency, but we'll also state that the intended function was to ensure a beautiful view, and that function has been met. But we also want to document the existence of a potential safety hazard. But in reality, no one would ever install a guardrail on this deck, despite it being code to do so. What we're really concerned about is houses that already have a guardrail installed, because there is an expectation of safety that should be met. Guardrail infill shall withstand a horizontal load of 50 pounds per square foot. No opening of the infill shall allow the passage of a sphere 4 inches in diameter, but a significant number of decks were constructed before these rules were adopted. So what do we do? As inspectors, we need to call out the deficiencies, but don't forget to think about the function. Does the guardrail move when you apply the slightest amount of horizontal force? Do we think that it could withstand 200 pounds of horizontal force? Does the guardrail feel safe for adults and for children? Then it's probably safe enough. Stair stringers should be a minimum of a 2x12, attached to the deck using a sloped joist hanger. Full width stringers are much stronger than notched stringers. Stringers with spans that exceed prescribed lengths should be supported by a notched and bolted post. If the height of a stringer exceeds 12 feet, then an intermediate landing is required. Here's some things to consider. Do the stairs feel safe? Do they have a handrail to grasp? Is there any movement or deflection when loading the stairs? Are there any visible signs of material fatigue or failure? If there isn't any movement in the stringer, then we should move to the tread. Stair treads should be able to resist a 300-pound load. 7 3/4 inches is the maximum riser height, and there shouldn't be a deviation of more than 3/8 of an inch in height. And 10 inches is the minimum tread depth. These considerations for stair treads are universal, and the average person can readily identify when stairs just don't feel right. So, if the stairs feel right, then they're right. It felt like we just covered a lot of code requirements, and we did, but since we don't know what code was adopted at what time, then the best we can do is inspect the deck for its intended function. There are many additional considerations that we have when inspecting decks, but unfortunately, we don't always see what we would like to see. We have never seen a flawless execution of water management when it comes to deck construction. In our high alpine environment, we have considerations that we would love to see addressed during construction that go above and beyond standard expectation for a deck's performance. But to be honest, we get excited when we just see the bare minimum even attempted. Some examples of waterproofing details in our area that get overlooked include not integrating the existing water barrier of the house with the ledger board, or at the very least adding flashing to the ledger board to prevent rot. Not providing a 1-inch gap between concrete and the wood, which will result in rot as the moisture trapped by the concrete is absorbed by the wood. Not managing water runoff that can erode footings during spring runoff season. Not sealing the end grain of pressure-treated lumber after cutting it. Not capping vertical exposed end grain, which will absorb water from snow as it melts and then crack as the sun sets and freezes that water trapped inside the end grain. Not using waterproofing tape on the tops of all beams, joists, and stringers to prevent rot and water absorption in areas where water can become trapped. Not sloping the deck surface away from the house, causing water to flood the home or become trapped as ice builds up between boards. Not using metal grates as decking material to prevent ice buildup under the drip edge of a roof. Not only is this a slip and fall hazard, but it also damages the decking materials during freeze-thaw cycles and during manual ice removal. Not installing graded stair treads that allow snow and ice to pass through the tread to improve winter safety. Not using hidden fasteners to secure decking to prevent rot caused by trapped water in face or edge fastened decking. Not reapplying protective paint or sealant regularly to prevent water and UV damage to decking and wooden materials. Not providing accessible options for snow removal such as snowblower storage, shovel storage, sections of guardrail that can be removed or opened for snow removal purposes. Not installing heat tape all the way down the downspout for gutters that will fill with ice during the winter season. Important details like water management are frequently overlooked, but surprisingly, engineered details that are outlined by the manufacturer or engineer are just as frequently missed. A specific type of fastener should be used with each specific type of hardware when building a deck. In general, every hole in a piece of hardware has a specific function and should be filled with a fastener. Using the wrong type of fastener will not only reduce the effective strength of the hardware, but it can also result in galvanic reaction, or in other words, corrosion to both the fastener and the hardware. If the fastener is made of a dissimilar alloy, or if the fastener does not have the proper types of coating, corrosion is inevitable. Nails and structural screws are designed to bend and deform before failure, which may provide enough of an indication to the homeowner that an issue is present before a complete structural failure. When installers use drywall or decking screws to install hardware, the results can be deadly since these types of fasteners will shear or fail instantly without any prior indication of failure. In addition to having hardware installed with appropriate fasteners, it's also imperative that you, as the homeowner, use the deck in a manner that it was intended. Installing a hot tub on a deck that wasn't engineered for the hot tub will most likely result in a complete structural failure. Most hot tubs can exceed 100 pounds per square foot, which is far beyond the strength of most decks. Additionally, decks are designed for a maximum occupancy, but if a deck is rated for 25 occupants, I can assure you that that deck is not rated for all 25 occupants to be jumping up and down in unison as the music for your birthday party is blasting. Although a deck can theoretically support a snow load without failure, it doesn't mean that the deck can support that load without damage. It is important to remove snow from the deck to reduce the likelihood of damage. Nature is relentless, And even if we do everything right as homeowners, all wood will eventually rot and turn to dirt. All of the metal components will rust and corrode away over time regardless of the special coatings applied by the manufacturer. And then there are the unforeseen issues like wildfires and insects. Oh, and if you have a tree growing through the deck, whether on purpose for aesthetics or by accident, just know a whole video could be dedicated to the types of damage trees planted near the home can cause. These are just some of the reasons why the average deck should be replaced every 20 years. But if you, as the homeowner, manage water that could damage your deck, apply protectants, store flammable materials away from the deck, store insect-attracting materials away from the deck, and keep an eye on the health of your deck and perform repairs as needed, then you should be able to double the lifespan of your deck. I know this video was long, and if you stuck in there, I appreciate you. Hopefully you learned something about inspecting decks. If you'd like to schedule a deck inspection, please visit 2moosehomeinspections.com. Have a wonderful day.